big clue you see there, Antonio? What's the big clue so we know what kind of problem we're up against? Your friends are saying the M. Would you go for that?
Yeah.
You should. Okay, because we're talking molarity here. As soon as you see molarity, okay, that's our equation of choice. You need to write that down, you need to know. Okay, now let's see what they're giving us this time. Well, it's a little different than the previous problem. In the previous problem, they gave us not moles direct, but they gave us a way to get moles, and they gave us liters directly. So we had this and we had this in problem 318. In this 319, it's a little different that we know the molarity this time. Andrew, this is for you. How many six? Three. Good job. Okay, now we know the liters. Can I get grams directly? No, but we can get moles. And if we have moles, we know we can get back to grams. And so on this problem, they gave us this, they gave us that. They're not asking this for this direct, but hey, we need it because if you have moles, you can always get to grams. So, Nicole, in row 3, how many moles of this stuff do we have? Yeah. The row 3, Nicole. Pardon?
I don't understand what
How many moles? In other words, solve this for me.
So we just multiply 0.0600 times 2.50.
Yes.
And I was doing it. So,
Okay, do it. Alex, do you already have it?
I got it.
Okay, hit it.
0.15.
0.15. How's SIGs on that?
So it'd be 0, 0.
Okay, do you want this much?
So just, okay, so it'll just be 0.150.
Yeah, because you're trying to hang on to 3. And Alex, is that what you got too? Okay, but now this is moles. That's not what they're asking. If this were a multiple choice test, I promise, one of the answers would say 0.150 grams. And I would sucker 1 or 2 of you into that because you saw it on your calculator. Just because you see it on your calculator doesn't mean it's the answer. So, we are here at moles. I need to get us back to grams because that's what it's asking. So, what is it I need, Russell, to carry on?
Multiply with formula weight,
And do you have the formula weight?
171.3
Okay, 171.3. And the units are what, Russell?
grams per mole.
Grams per mole. Mole up here, mole down there, gives us grams. Okay, later today when you're looking through your notes, this is the number you're going to say, where did that come from? That's the formula weight that Russell did for us. That would be 1 barium, 2 oxygens, and 2 hydrogens. And so we multiply that out, we want to hang on to 6. Pedro, what'd you get?
25.7 grams.
25.7 grams. Yeah, Bruce?
I got everything except for, where did you get the 0.150 moles from?
Because Nicole and Alex multiplied that times that to solve for the moles.
Okay, so they solved that. And that's
They
what
solved
oh, yeah,
that.
okay,
This,
okay.
they solved this, and then we took that into the next part to get it into the units we
Gotcha.
want. Okay, are we all right on that? Yes, ma'am.
I kind of like, what I did, I got the same answer, but I kind of just, I knew we were supposed to multiply by formula weight, so I didn't bother with that. I just multiplied the 2 that I did and got 1.50,
Okay.
and then
You
multiplied
could do
formula
that.
weight. Just,
You could.
is that okay?
Sure. If you get, see, what she did, she kept this running up here. Instead of taking the time to write this down, she just went right on with it. What I prefer to do just in class, because some people can get lost in the steps so easily, I like to say, okay, let's get an answer here. Let's see the answer as a checkpoint. Then, really, a step 2, then they say, oh, that's what you have to do to get back into grams. So all the time we're doing this, this is why a good 85% of the people do better on the final than they do on one of the 3 tests, because, like test 1, we're hitting this stuff over and over as we go through. Grams to moles, moles to grams. If you didn't have it the first time around, you got great opportunities. You know, get it now if you missed it then. All right, are we okay on that? That was section 6, and that was one big long section. Okay, let's move into dilution. Let me see if I can convince you of this. Just listen to the story. Let's say you do have a sore throat, and you think instead of the hot salt water, you need vitamin C. And so, on your way home from school today, you're going to swing by the pharmacy or the grocery store, and you don't want to take tablets of vitamin C, but you decide if you drink orange juice, that's going to get you vitamin C, and that will cure your cold or sore throat or whatever it is you have. So you stop at, it'd have to be grocery store, I guess, and get yourself a can of the frozen concentrated orange juice. I don't know, does Walgreens carry that kind? I think they do have a frozen thing. Okay, wherever you stopped, you got this can of concentrate. Okay, let's just say for discussion, in this can of frozen concentrated orange juice, there is 1 gram of vitamin C. And you need 1 gram, and that's going to cure you. So you take that home. Now, you got the idea, the active ingredient, the solute we care about is the vitamin C, and we got 1 gram in this canister. Okay, you get home, and you just want to ingest that 1 gram of vitamin C. Okay, you could take a spoon, and you could just eat the frozen concentrate. And then probably you would have your cold, plus you would have a stomach ache as well. Okay, but that would get you the 1 gram of vitamin C, right? More likely, you're going to take that concentrate, dump it into a pitcher, then dump in 3 cans of water, okay, stir it, tilt it back, and chug the whole thing. You have still just ingested 1 gram of vitamin C. That's the dilution idea. The basic premise is, okay, when you dilute something, just by adding solvent, usually water, the amount of solute doesn't change. Now, the volume changes, the concentration changes, but the amount of active ingredient doesn't change, because all you did was just put in some solvent. Okay, let me show you mathematically what that means to us. Okay, we start with our frozen concentrate. And in that frozen concentrate, we have a certain molarity of vitamin C, the initial concentration. You have moles of solute, moles of the vitamin C, over liters of it in that canister, and that's going to be the initial volume. Okay, you take that, you dump that can into a pitcher, and you dump your water in there, stir it up. You have a new molarity. And you have a new volume, right? Well, let me rearrange a little bit. And you don't need to write this down, just follow the math. Because when I get to the end, I'll say, this is what's really important. Okay, I'm going to move the liters to the other side. So I have M1L1 is equal to moles of vitamin C. I'm going to do the same thing for this one. M2L2 is equal to moles of vitamin C. Well, look where we are. We know, I convinced you all, I hope, these are equal to each other, then these must be equal to each other. And so let me rearrange. And I have the initial molarity times the initial number of liters is equal to the final molarity times the final number of liters. That is a mathematical statement of moles of solute equals moles of solute, based on molarity there. Now, your textbook doesn't leave it quite in this form, because since we have volume and volume, as long as I'm consistent, I don't have to be in liters. Okay, now, that's a sticky point. If you are only doing a molarity problem like that one, we have to be in liters. Excuse me. But if we're doing a dilution, because volume shows up on both sides, this could be in liters, Or if you have both of them in milliliters, that will work just fine. You can have both of them in quarts if you wanted to, and it would still be true, as long as you're consistent. So, this is what your book does. M1V1 is equal to M2V2. Anytime we dilute, this is what you need. Now, where did it come from? That basic idea, dilution changes volume and concentration, but not how much solute. Let's do, yeah, Andrew?
Did you say that right there where it's moles of vitamin C and the moles of vitamin C, those are always equal to each other?
If you got the same solution you're working with.
Okay, because I was going to say, 'cause if you had a different amount of liters, you know, it'd be different, right?
Well, I diluted it by adding more to it. Let me get this up and then let me address your question. Okay, on this example, here, I can't take, okay, here's solution I got in the laboratory here. Here is an independent solution over here. It's not true to say molarity times volume of this one is equal to molarity times volume of this one. This is only true, you start with this concentrated stuff, like the vitamin C, the canister, and you just add water. It's
I
got
know
to
the
relate to
moles.
each other.
Okay.
You got to have the
Yeah,
same
the moles.
solute, same solution, you're just
Okay.
putting in extra water. Okay, now let's read this. And to me, I mean, that's just the basic equation we use, and dilution problems should be easy, but I know from experience, it's sometimes difficult for people to decide what they're up against. So let's read this together very carefully. How many mils of 18 molar sulfuric acid are required to prepare 1 liter of a 0.9 molar solution of sulfuric? Okay, I see molarity. So I might think, there's my little equation I need. But there's something more. There are 2 molarities they talk about. They have a high molarity. They have a lower molarity. That's what just shouts, it's a dilution problem. We've got 2 molarities in this problem. Or it may have some wording about dumping in some water. Andrew, do you have your book for that one? Read that one and see how different the wording is in the book than this one. I may have stripped this to bare bones.
How many milliliters of 18.0 molars of H2SO4 are required to prepare 1.00 liters of a 0.900 molar solution of H2SO4?
And that's all. Okay, I took that one word for word. Okay, so they didn't throw in any extra at this temperature, at that temperature, so it's identical. Okay, when I look at that, I see the molarity, but because I see 2 molarities, I know we're talking dilution. And so this is your initial stuff, this is your final stuff. Okay, our initial molarity is 18.0. Now, our initial volume, that's what we need to know. Because it says how many mils of that 18 molar. So it's going to be V1 is what I need to know. Okay, now, we know we need a 0.900 molar solution, and I need a liter of it. So if I put this in liters, then this answer is going to be in liters. Now, I will get the same answer if I go with milliliters here, then this will be milliliters, but it's going to be the same amount. Let me show you what a practical problem this is. Okay, this is the 1 liter volumetric flask, just like this. Okay, I want to end up with a liter. So this is what I would use. So it's really a question. I've got this really super concentrated sulfuric acid. Because we always buy our acids and our bases also as concentrated as possible, because we don't want to pay shipping on water. And secondly, if we buy them super concentrated, we have such versatility. We can dilute them at an infinite variety of ways. So we just stock it really concentrated. So I need to know what volume do I need to put in here. Don't think safety yet. Okay, just what volume of this do I need to put in? And then I'm going to add water, the solvent, up to this line where the bottom of the meniscus is right on that line. Okay, so it's a dilution problem. Biologists do this kind of stuff all the time. And so we're going to solve for V1. So we have 0.900 just times the 1 divided by the 18. And Andrew, what did you get for V1? 0.500
liters of H2.
Okay, now, is that what everybody got? That sounds like a decimal
I
is.
trimmed it in my head.
Okay, your head didn't work this time.
0.05.
Points, you were close. 0.0500 liters, but because our,
I did 9 divided by.
oh, okay,
0.9.
0.9 times 1, there's the difference. Okay, but you know, our graduated cylinders, our little ones, aren't measured off in liters, they're measured off in milliliters. So what is this in milliliters? Anybody, just shout it out. Metric conversion, how fast can you do it? 50.0 mils. Okay, so what this tells us to do, and this is a very practical problem in the laboratory. Ruben should take 50.0 mils of this really concentrated acid. Put it in here, and again, we're not thinking safety yet. And just add water slowly until the bottom of the meniscus is right on that line. Okay, now that's in theory. In practice, is that the way to add acid? What's wrong with that, Brittany?
Water to acid.
Well, that's what I just
I mean,
did.
the other way around.
Yeah, add acid to water, AA, add acid. So, what would we really do in the lab?
Fill it.
Yeah, you'd fill it, you'd put in quite a bit of water. Okay, now you can't get too close to here, so yeah, we gotta violate some safety stuff, but we're gonna put in a lot of water, and we're gonna slowly add our 50 mils of concentrated acid, add a little, stir it, add a little, stir it. Then after you've added all 50, then we gotta top it off with water to get up to the line. So you never ever measure the water, you just add it until the total is up